Hello, welcome back. We have, at this stage of the course, finished all of the individual unique methods that we'll be covering. So this week and next week we have a we're kind of stepping back into broader topics again, not delving into the nuts and bolts of any particular method. This week, the main thing is this is setting up for the last lab that you will be doing. I'll have that up on eCampus in the next day or two. The last lab is where I will be giving you a series of questions. And I'll be giving you data, and I will not tell you how to do it. So you would then have to be able to remember and recreate what you did and properly identify the correct technique. That is the main thing for here, focusing on what the correct technique is and for a particular question, and we'll also be looking at the presentation of combining different techniques into a single report, as that will also be part of that final lab. So starting with the how do we answer that question of what technique do I want to use? And I will tell you right now that a fair amount of where I'm getting this from for today is right in the front cover, not the first page, but the actual front cover of the textbook for this class. This, not exactly a page, as it's the front cover, is in fact a very useful resource for this sort of thing. So if we go back and think about the general structure, that framework of conducting an analysis. Where we had our general problem, the data collection, as you may recall, could be in a few different areas. I'll put it here. At that point in time, we can have where we get our specific question and we make sure we have that specific question in the format that we can structure it for a null hypothesis and an alternative hypothesis. The form of this question, and perhaps to a lesser extent, it is brought out in that front cover, to a lesser extent, the form of the data, the type of the data informs then what method we're going to pick. So the first thing we can be looking at is what kind of question are we working with? Just as a recap, we have seen a few different kinds of questions throughout the course of the semester. The first broad topic or group of methods we saw was comparing the means of different groups. And we had two different general tests in that. If we had 3 or more groups, we would use ANOVA. And we have, for 2 groups, a t-test. The t-test for, strictly speaking, for 2 groups, we had 2 different kinds. So 2 sample, and the question there is whether or not we had the observations matched as pairs. So, say each county within the elections, there's an example from the labs in 2012 versus 2016, or 2012 versus 2018. Comparing 2 years, we could match Mon County's older result with Mon County's newer result, Preston County's old result with Preston County's newer result, Kanawha County's older result with Kanawha County's newer result, and so on. When they can be matched like that, it's paired. If instead we are comparing, say, Pennsylvania with Ohio, or West Virginia with Ohio, I can't match up, say, Stark County, Ohio, directly with anything in West Virginia. So they're unmatched and don't even have the same number of counties, 88 versus 55. So then it's a 2 sample test. The other, somewhat related, we had the third kind of t-test. A 1 sample t-test if I'm comparing the group mean, say the average, some income, the average vote total, what have you, for all counties in West Virginia against some other value, against the national average perhaps. And that would be a 1 sample t-test. Somewhat related to t-tests, uses a somewhat different distribution, but if we're comparing an individual observation, whether it fits in with the group, or is it an outlier, we would have then a z-test. This one, the difference here, this is a group mean. T-tests are always about an average. This is, does Mon County's value for something fit in with the rest of the state or not? Depending on where you're at in the lab work, at one point you may notice Mon County has a really, really low median age. This is not a surprise given the influence of the university, but we might say, is it so low it's an outlier? It probably is. And we could do a z-test to check against that. and that's comparing Mon County with the distribution of the rest of the state. Therefore, it's not comparing against any particular average or mean, which is the difference between these two tests. The t-test, the z-test, they have one additional choice to make. The one-tail versus two-tail distinction. A one-tail, you're only interested in one direction, you're hypothesizing one direction. So to say group A is more than group B, we might say something like, okay, this was in a quiz or something, or the exam recently, if I'm comparing two states that had different policies regarding COVID, Tennessee did not introduce social distancing early, Kentucky did. So I would hypothesize that not only is the average COVID rate for the counties different, I would hypothesize that Kentucky is better off. And I'd hypothesize a direction. If all I want to do is to say, are they the same? So, is, say, New Jersey's rates similar to New York's rates? Yes or no? All I care is that, are they similar or are they not? In that case, I would just use a two-tail test because I'm checking to see if they're the same. I'm not that interested in whether New York or New Jersey has a higher rate. So this is, except for the z-test here, about comparison of group averages. So if your general question is trying to do that kind of comparison, you can now narrow down. It's going to be this. It's not going to be regression. It's not going to be Moran's I. Comparing means is going to be t-test or ANOVA based upon how many groups you have. Another set of techniques that we saw was point pattern techniques. Yes, I know I'm skipping over chi-squared, I'll come back to that. Another technique was point pattern. This would be questions of, are the locations of those points randomly located? Are they clustered? Are they evenly spread out? The point here is about the location. We're not doing anything with any value, any attribute of those points, just the geometry. And we saw many different types here. And we saw, based upon the two assumptions of complete spatial randomness, that points are located independently of each other, and that points are equally possible anywhere in the data set, in the study area. If I break the second of those rules, I can use a distance-based. They're going to be closer together if there is some kind of attractive process making them not independent of each other. Or they'll be evenly spaced if there is some repulsive process pushing them away from each other. Either way, they are not independent. We saw the R statistic and Ripley's K function as examples of that. The density-based approach, looking to see if there are parts of the study area which have a denser than expected number of points, uses quadrats. And we saw how to analyze quadrats using a chi-square test. The main thing here is I have highlighted the locations of points, are they random or not. The other difference between them, not just the density and distance based, what may help us decide which one to use, if I'm interested in just are they random or not, I could use quadrats. But if I want to make sure I can distinguish a clustered pattern from an even pattern, I need to use one of these. So that is point pattern as another category of tests to answer a different type of question. The next technique is not statistically related, but you might think of it the same way, is spatial autocorrelation. Whereas point pattern was about are the locations random, this gets to attributes. So now instead of the location, I'm interested in the attribute. And typically we're interested in positive spatial autocorrelation and expect that. Of like values are similar to each other and close to each other, where Mon County and Preston County, they're close to each other, they share a border, or they are within a distance threshold, or they are within X nearest neighbors of each other. No matter how we are defining the neighborhood of a county or an observation, Are they similar to each other? That would be positive spatial autocorrelation. Or are they notably dissimilar from each other? That would be negative. The other thing is global versus local. Do I want to have a general picture of the whole study area, the whole state or the whole country? If I am, and we know this for COVID-19, but if we saw a new disease emerge, I wanted to know, is it infectious? We might be wanting to see a global spatial autocorrelation test, just to say, are they close to each other? Are they high values located next to other high values, low values near other low values? If that's the case, we might conclude it's infectious. To make that determination, I don't care where the clusters are. I just need to know if there are clusters, period, end of story. Local, on the other hand, now I care where the clusters are. I want to say, okay, I know there is a high cluster in this part of the country, around New York City. I need to send supplies there, I need to send ventilators there, what have you. So the question of, do I need to know where the clusters are, basically, decides global versus local in Moran's eye, in spatial autocorrelation. As an aside, there are other tests for spatial autocorrelation. It is not just Moran's eye, but that's the one I have covered in this class. So these would be, as I have here, asking questions about, are the values related to each other? Are they near each other? If they are similar. The next, or another general set of questions, and the last ones we saw, are looking at the relationship between two variables. The first thing we saw in this general context was having a very specific set of two variables. If we have a set of observed and predicted values, and I want to assess, are my predictions good? Then we had chi-squared. In this class, we predominantly saw this. You didn't have a chance to do it in a lab in this context, but you did have the chi-squared lab. You did not have it in the context of the point pattern, analyzing quadrats to say, I am predicting through the assumption of complete spatial randomness. How many cells have no points? How many cells have 1 point? How many cells have 2 points? And so on. Are those predictions correct? That's where the chi-squared would come in. If I'm just comparing 2 or more attributes. This is what we saw most recently. That's regression. Linear regression, ordinary least squares, OLS. You may often see tools named OLS to do this. We could have one independent variable used to try to understand and analyze one dependent variable. That would be bivariate regression. 2 variables, one independent, one dependent, bivariate. Or many independent variables related together with a single dependent variable. That's multivariate. So in both cases, the questions we're looking at are these attributes at the same observation related to each other. It's important to note that they have to be with the same observation. There's no point in trying to do a regression of incomes in Ohio against voting patterns in West Virginia. They're just, why would you bother? It would be income in the place against voting patterns in the same place. If there is something spatial or geographic about this regression, there's several different forms actually that we could use. I have covered 2 in this class. The spatial error regression, if I think that there is some missing process that in my bivariate or multivariate regression, I have some unaccounted for factor that creates a spatial pattern in the dependent variable. Then I could use a spatial error process. If there is a spillover, so that the dependent variable itself automatically would display spatial autocorrelation, essentially, then there would be a spatial lag regression to directly incorporate and model the effect of the dependent variable in one county or observation on the dependent variable of its neighborhood. So that's a very quick overview of the different techniques here. I've already asked you questions like this on the second exam. I can tell you right now that the last quiz number 7, is going to be a series of questions and you identify the technique that would be best to answer it. There may be multiple correct answers. Like it could be a question that could be answered with any of the point pattern analyses. But it will be that kind of matching question. So to practice that, what I will do here is, first is I will give a few examples. I'll pause and just stand here and then explain which I would use and the rationale for picking that technique. So the first one, if I were to want to understand, and I'll keep these all within kind of tree ecology type scenario. If I wanted to look at the density of trees across 3 different landscape types, across wetland, deciduous forest, coniferous forest. So different patches of landscape and the density of trees. What would you use? Okay, even though it is looking at the density, that might lead someone to suspect point pattern. However, I was very clear about it being across 3 categories. So I'll have a bunch of different wetland areas, a bunch of different coniferous forest areas, a bunch of different deciduous forest areas, and I want to compare the density, perhaps the mean density across all of those groups. That would lead me to ANOVA. So I would pick ANOVA. And it's important to note there, I did not, when setting out that question, I did not directly say group mean or group average. You would have to recognize this is something where having the group average is a way to get to answering that question. So the questions, and this mirrors what could happen in a real world scenario, the questions may not be directly guiding you towards, it is going to be this technique, and be that clear. So now another one. I have measurements of the height of a series of trees, and I want to know if tall trees are near other tall trees, and maybe they are having to grow tall to outcompete each other to reach the sunlight. So I want to know if tall trees are found in groups near other tall trees. Okay, for that, recognizing I'm looking at the height as an attribute of the tree, and I want to know if there's a spatial pattern of that attribute. That would lead to Moran's eye. An important note here, the examples we saw in the labs about Moran's eye were counted with polygons. Moran's eye can apply to point data as well, like the locations of trees. You just can't use a contiguity matrix because points don't have the ability to bound each other, to be neighbors with a common boundary. But you can still look and say, I want to compare against the 10 nearest trees and use a nearest neighbor matrix. Or I want to compare against all trees within 100 meters and use a distance threshold matrix. So Moran's eye can be applied to points as well. Just because the geometry of something is a point does not guarantee it will be a point pattern analysis. After all, point pattern is just the location of those trees. Okay, now for a third technique, a third question. I have a series of variables of the tree, not just their height. But I might want to know more about what creates what affects the height of the tree. So I want to understand the relationship between the age of the tree, the altitude of where the tree is, so its elevation, the aspect, so is it facing south, north, and so on, and incorporate the height of nearby trees. So I have those 4 things: the age, the altitude, the aspect, and the age of nearby trees. To understand, or not the age, the height of nearby trees. To understand the height of a given tree, what technique would you use? Okay? We might initially think multivariate regression. However, I intentionally put in the height of nearby trees to understand the height of this tree. Kind of goes off of the Moran's eye thing I had before example of, are they related to each other? By bringing in the neighbor's dependent variable as essentially as an independent variable, that leads to the spatial lag regression. So as a very particular example, going to spatial lag regression explicitly. So those are the kinds of questions that could be, they will be on quiz 7. You will get plenty of those on the final exam. And that will be a key component of the final lab, being able to identify the appropriate technique to answer a given question. The other part of that lab is taking the results from several different techniques, 4 or 5 different techniques, say, to integrate them into a single coherent presentation. So we might be interested in a particular set of processes. So I'll keep on with this example, the tree height. So my overarching question might be, what enables trees to grow taller? And I can have different questions specific to aspects of that broad process. I want to say, is competition a factor? That if one tree is tall, that competition between different trees means its neighbors are guaranteed to also be tall. And I can use Moran's eye for that. And I'm specifying here other attributes being a factor of specifying interval and ratio. It's not exactly this as a strict order, but typically the independent variables and the dependent variable for regression are interval and ratio. At least of the forms and approaches to regression we have seen in this class. With the first thing I said, looking at the different type of forest or the land cover, is that a factor? That can be answered with ANOVA because land cover, not continuous, not interval or ratio, it is instead nominal. I have groups of land cover then based upon those different nominal classes. Lastly, I might want to ask the question, say, land cover being 3 different ones, I might say I might categorize it instead into 2 groups, north and south facing slopes. If that's a factor in the height of the tree, I can use a t-test. Now in terms of presentation, these are all giving, in a sense, different views, different facets of this broad process of what makes a tree tall. I have, in a sense, been conditioning through the structure of the report towards a broader idea. We start with an intro which sets out the problem that says, I am interested in understanding the processes that affect the height of trees. Within that, I have a series of hypotheses. The end of that introduction would often be saying, here are my specific hypotheses. I hypothesize tree competition is a factor. I hypothesize 3 other factors, 3 other attributes are a factor. Say the age, the altitude, put aspect over there, so I might say the age and the altitude and the distance from a stream. And put that into regression. Or I can say the age, the altitude, the distance from a stream, and if I find this to be a significant Moran's eye, I can say, well, okay, maybe I want to incorporate the neighbor's tree height and do this as a spatial lag instead of just as plain multivariate regression. So we have that hypothesis. We can say I hypothesize land cover is a factor. I hypothesize the aspect is a factor, and I've categorized it into slopes facing north versus facing south because I think those facing south getting more sun would be higher. So I might then say is a, not just a 2-sample test, but a 1-tail 2-sample test. And here's why I think it's going to be 1 tail. We have a methods section. I want to justify all choices in the techniques of how I am answering these specific hypotheses. So you have to make sure you relate the method here to the hypothesis here. If you're doing a method that doesn't answer those hypotheses, don't do it. It's not relevant. But as I mentioned earlier, we can say I might say, okay, if I is significant, do a spatial lag regression. So I can use the results of one technique to inform choices about others. You would then have a results section. In that results section, you just present the facts. You say, I start here. We might present them kind of in the order that they occurred in class. We might start and say, okay, here's the t-test for north-facing versus south-facing slopes. As with the previous labs, we don't typically give every single piece of information that Excel or whatever other software suite has provided. We pull out the important information and only tell the reader, whoever that reader may be, a scientific audience, a professional audience, a boss, whoever that audience is, we only tell them what they need to know. And I would say, okay, here is that relevant information from the t-test in the table, and explain, here's what I found. I found that because the p-value is pi, the p-value is 0.43, in fact, aspect as categorized by north-facing versus south-facing slopes, not that useful. It is not a major factor in determining the height of a tree. I can then go and say the ANOVA by the land cover. It may be a factor. It was significant. I followed up with individual pairwise comparison t-tests group by group, and I found that the average height of the deciduous trees and the average height of the coniferous trees were about the same. However, the average height of the trees in the wetlands was lower. So I find there that information, and I just say, here are the groups, here's what was higher, here's what was lower. They were significantly different from each other. I find Moran's eye is significant, suggesting that maybe competition is a factor, or saying trees within 100 meters have an effect on other trees. And lastly, present the regression. I present the table as in the most recent labs, 6 and 7, that says, here's the coefficient, here's the p-value, here's the overall R squared, or the overall other summary stat, the AIC. And say, these are the significant variables. Age was related. Distance from stream was related. Altitude was not related. So I might find that. And that's what I present, and that's what's in the results section. It is just those outcomes, just that description, and in the brief explanation, pulling out the important and pertinent facts from the tables for the reader that informed you as the author in this next step? Discussion. What did you learn from the results? So you might then say, here's what I found are important factors for the height of trees in this experimental forest in West Virginia. And you say, here's what I found, and I found that aspect turns out not to have been a factor. Wetland cover is. That the wetlands, something about the wetlands, and you might then hypothesize what that could be. The soil being too waterlogged might impede nitrogen uptake. I don't know if that will be the case, but that might be some possible reason as to why trees and wetlands might be shorter. You find spatial competition. Yes, there is some kind of process going on. And you say, there's probably that competition where the taller trees, they're getting more of the sunlight resource for tree growth, and if a tree is going to be successful nearby, it must also be tall to compete against its neighbors. And you find out, okay, age is a factor. Distance from stream is a factor, where as long as it's not waterlogged as a wetland, being near the stream provides moisture to continue growing through drier periods, and those become taller. Older trees are taller. You find that out, probably not surprising. You find elevation is not a factor. And that's something where, what did you learn? You might say, I expected elevation to be a factor and it actually wasn't. But, here's the thing. I can only draw conclusions from any of my techniques about my study area. You hope that you can generalize beyond that, but there are limits to that. You know you have just a certain amount of data. Altitude certainly is a factor in some place like Colorado, in the Rockies. As you get closer to the tree line, the trees get shorter. But in most of West Virginia, our mountains are tall enough to get to a tree line anyway. So altitude may not be a factor in West Virginia where it is in other parts of the world. So you have to be careful when you say elevation is not a factor in tree height. Well, there are some places where it is, just not where your study took place. The other thing there, what do you do with the results? And really this will lead to next week's video topic, statistics and society. But what do you do with the results? As we saw at the very, very beginning, we are communicating our results to have some kind of effect on others. That could be affecting a policy, that could be guiding some kind of decision. It could be furthering scientific advances in knowledge. For something like this, there could be, depending on the questions, there could be that scientific advancement. It could also be to help tree conservation efforts throughout, say, a state forest. And you might say, okay, here's where, if we're going to assume tall trees are healthier, maybe, maybe not. If we're going to make that assumption, we can then be able to say, well, if I know what factors create that kind of outcome, I might say the parts of, say, if I found that distance from a stream is a major factor in promoting the height of a tree. Okay, so my conservation efforts, my efforts at boosting tree health and tree growth need to go elsewhere. Don't bother going near the streams, they're already doing better there. Land cover, okay, there's something about the wetlands. Then maybe I want to make sure that those trees get special attention. Now to illustrate, what do you do with the results? That is a factor of the audience too. What's important in these processes for a state forest or a state park could be different from a timber company. The timber company may want to know, okay, I want to go know where the tallest trees are so I can cut them down, get the most timber. Now, okay, I'm interested in focusing on, okay, near the streams, they're going to be taller there, make sure I go there. I see that wetlands are a factor hindering tree growth. Maybe I need to do some tree modification to drain the wetlands so that the soils are not as waterlogged and the trees can grow taller. So what you do with the results truly is a factor of who the audience is, what you are trying to accomplish. And lastly, these four, we may have a conclusion section. Which kind of just sums up everything. The bottom line of what you learned, in a sense. We go and we do, even if we have multiple questions, they're integrated. So I have the intro leading to all the hypotheses at once. I present all the methods at once and justify those choices in a single block. I present all the results after the methods. So it's not a piecemeal, here's the t-test part. Intro, methods, results, discussion of t-test. Then an ANOVA part, intro, methods, results, discussion of ANOVA. That would be very choppy. It would probably be harder to read, and especially it would not allow this kind of integration of here is what I learned about the process writ large by combining these different techniques and combining these different perspectives. To be able to accomplish that combination, that fuller picture by seeing the whole rather than just the parts, we present them as that integrated whole, not part by part by part by part. So that should hopefully set you up well for everything you would be doing in the last lab, both choosing a technique and doing a quality write-up, a quality report at the end of it. So that ends this week's topic. As always, if you have questions, feel free to email me, feel free to use the discussion boards, and also, as always, please make sure you have are staying safe, are staying healthy, and keep washing your hands.